Hi everyone, thanks for coming out. Today I'm going to talk about deep learning for a time series in practice. I guess just a little bit more about me. I've now been working with kind of time series and using deep learning on it for I think actually like 6 years now maybe. Ever since I was back in college was when I first started playing around with deep learning models on time series, and since then I've used it in pretty much every job I've had. Used it to forecast healthcare data, patient length of stay, used it to predict demand in retail stores, and now using it to do anomaly detection on cybersecurity data. So it's definitely been a long way, and I at least like to think I've learned something about it along the way. So anyways, let's get started. So first thing, I'm the author and kind of creator of a deep learning for time series forecasting framework, open source. I hope everyone checks it out after this. A lot of the examples will be using it. It's called Flow Forecast because I actually originally created it to forecast streams and river flows, but then I generalized it to work on any type of temporal data. So obviously I think one of the top deep learning for time series frameworks out there. The best in every way. No, just kidding. There are plenty of good frameworks out there, but I do think we're unique in how we use configuration files and make it easy to spin up different experiments and test lots of different models and different configuration settings. So yeah, I do hope you'll check it out afterwards. Okay, so overview of the tutorial. First, I'm going to go over some background. Then I'm going to go on about challenges and obstacles before we jump into some coding examples. Because there are lots of challenges, I think, that particularly when using a deep learning model, I guess it's true in most time series problems in general, but particularly using deep learning that people sometimes overlook and don't think about long enough ahead of time. So then that leads to problems down the road. Then I'll go into the tutorial section and go over a couple different tutorials, maybe even add in one there depending on time. Then I'll discuss some future directions, kind of where I think the field as a whole is going, and kind of what I think that means individually for people in industry, and how to keep up. And then we'll have a long kind of Q&A because yeah, I don't think I'm going to go over an hour probably, so we'll probably have a lot of time for questions at the end. So some brief history. I always like to think about things historically, like even like 6 or 7 years ago, basically all that people weren't really looking at deep learning for time series, and if they were looking at basically just LSTMs and GRUs. Over time, as kind of the NLP field as a whole has progressed, I think the talk before me talked about NLP a bit too. More of the NLP techniques have kind of crossed over, which kind of makes sense because they're both kind of sequence models in a respect. So more ideas like attention, and then later on transformers being added. And now, most recently, we're seeing a lot of graph neural networks. Unfortunately, they're still very hard to use. But yeah, it's kind of advancing along that way. Not that, and one of the things too I think is interesting in time series, and we'll get to, is none of these techniques are really obsolete because time series is a lot more fragmented. Some of these things, like sometimes an LSTM might be the best thing to use, or a GRU, which I don't really think is the case in NLP now. Usually you're always going to use some BERT model or some variant of it. So yeah, we'll go over that. So now some challenges. Obviously, formulating the problem initially is a very hard thing, and I'll get to that in a second. Then, picking the right model since it is a more fragmented landscape. Fitting the model, always tons of issues, and finally ensuring the model is robust. All these are fairly difficult things, but we'll dive into each individually. First, I'll just clarify a bit of terminology. I bet most of you are probably familiar with this, but Forecasting, we're generally trying to predict the target variable at a future time step. It could be 20 time steps into the future. At each time step into the future, you know, up to 20, it could be variable length, but we're trying to predict the actual value in general. Or there are some times when you assign it to a quantile, like with a quantile loss, but generally we're trying to predict the actual value. In classification, we're trying to label, assign a label to kind of a sequence of different time steps. In anomaly detection, basically it's just a extreme case of binary classification, but it's treated a little bit differently in terms of what loss function and other stuff you might pick. And it's often treated a bit differently in literature and types of data sets. And yeah, there can be overlap between these, and you can do these jointly, so we'll get into that in a bit. Okay, so yeah, I mean, one of the first things I think for an industry person to think about is how will, realize I didn't type that right, but oh well. It should be how will myself or my customers use the output of the model. So that's kind of the big thing, because like of course on a lot of the, you know, these state-of-the-art models you see coming out of the major research conferences, they're just trying to beat some pre-established benchmark, so they don't really think about that too much. But this is of course really important and the kind of the central thing. So and particularly in forecasting, I've seen a lot of times where like we optimize models to try to predict the exact value, but in actuality, basically a range of values it could be in is more useful. You know, I worked for a bit doing COVID forecasting with an epidemiologist, and it was much more important to see kind of what range it would be in at different times and what the underlying drivers of that factor were than the actual value. So that's always something to, I think, to think about. Then also like kind of the properties of your data. Like we generally deal with very messy data sets. And so there are a bunch of things that can throw off kind of the neat kind of picturesque forecasting model or classification model. You see things like variable length sequences, irregular sampling, and large amounts of missing values can all be kind of issues. So those are all always exploratory data analysis is useful in kind of this respect. Likewise, another thing we face is how to incorporate additional information, because like again, most of these benchmarks, there's an existing data set, you try to beat the benchmark on that data set. But in reality, like in kind of real world problems, we have a lot of auxiliary data we could incorporate and a lot of additional features we could incorporate, and it can sometimes be hard to think about how to do that into kind of different fixed size deep learning models and how to create, do I create an embedding, do I do all this? So this is all something that is good to think about. I don't have an exact answer of just how to do it, but something to think about when doing time series forecasting or classification in industry. Okay, here's where I was going to first get out of my slides. So basically, as I was saying before, the time series forecasting landscape is kind of fractured. This is already somewhat of an old study, but like I found it really interesting because you probably want to see something similar in NLP. There's this thing called the Monash or time series forecasting repository, which showed different models and their benchmarks and stuff on different data sets. So there are a whole bunch of different data sets here, and you see different deep models and kind of vanilla models. And so different deep models perform better on different data sets. It's the bolded model. I mean, I'm not going to go over each and every one of these, but just by looking over this, you can see it's very fragmented which models. There's no single model that seems to outperform every other model on data sets. And likewise, just anecdotally, I've seen times where like a simple model with attention like works better than a really big transformer model. So that's definitely something to, I guess, think about. And look into. So, okay, just a framing problem. Okay, so yeah, a case in point was the Informer. It was a new state-of-the-art model released at AAAI 2020. It won the best paper, so I was like, it must be good. But I quickly found myself banging my head against the wall trying to get it to work to actually produce usable forecasts. So yeah, so for instance, with that, basically, even though it was state of the art in that respect, oh, by the way, with flow forecast, as I'll get to in a bit, we log all the results. All the results get logged to weights and biases, which is an experiment tracking tool. So see, like the forecasts with it were just basically, even after a lot of hyperparameter tuning, they were just kind of awful. So anyways, but I was, oops. I need to figure out how to get back to the regular slide. Until I haven't been presenting much lately. Oh, there. Yeah, I was determined to use it, but eventually, and I even bypassed simpler models, like for instance, RNN, which is just a simple RNN with attention. I think I have some examples of that too on weights and bias. Or yeah, this one I think. You know, even though that out of the box kind of worked much better. Oh wait, this was that model. I had the example there. Oh yeah, so see, this was what DNARNN produced. Obviously, a lot better. Though as we'll go into a bit, it wasn't actually doing everything right, but just out of the box, it worked a lot better. But I was so set on using the Informer that I wasted tons of time and hours thinking, oh, this should be able to outperform this model because it performed better on these experimental data sets. So that's just kind of a case in point of something not to do. Common issues. Oh, common issues when training the model. Oh, I don't think I actually incorporated the link on here. But some common things I see. This is actually one of my most upvoted, I think, answers on Stack Overflow ever. So I take some pride in it. But basically, common things people run into, and this person was actually asking why their training loss was NaN for an LSTM, was the biggest one is always check your data. You want to always ensure that there are no missing or null values, because like in a neural network, even a single missing or null value will cause all your output of the neural net to be null, and depending on what thing you're using. The other thing is you generally always want to scale your values, because if you pass in really big time series values to a neural network, over time it will cause the gradient to explode, and at that point you get another error, which is usually infinite losses, which I kind of note there. Lower learning rate, as we'll see, generally works better. So I usually start with a lower learning rate, and I might turn it up. Yeah, the reason I bring this up is just because these seem to be common pitfalls that happen to people a lot. We do have some automated checks and flow forecasts, so these don't happen to you there. But if you are training a model outside of our framework, or I think there are even certain times even in our framework, these we don't catch necessarily all the messy data. These are very common things that can go wrong. So common issues, yeah, I should put a link there. The other thing is metrics alone don't mean your model will perform well. Basically, and I've seen this happen a lot. Basically, actually just based on that other, application error. Throw that up there. Well, this was, oh wait, yeah, I already had this tab open anyways. So yeah, I kind of wrote this report on forecasting this river flow. And so these models did, some of the models at least seem to perform well at forecasting, but actually when including this model, when you look at what they're actually looking at in terms of features, and this is a feature we automatically build into flow forecast, is these shape plots. You see that none of them are really using precipitation. And this somewhat makes sense because in this data set, this is kind of a river essentially in the desert and it doesn't normally rain. But you can see none of the models are really learning that precipitation is something to factor in when forecasting. They're mainly using the temperature, the existing CFS, and the dew point. So that basically when you do have a large rain event, you have a large rain event where basically the river, where the river shoots up to a really high value at once, the model doesn't really respond accordingly. And even though they model kind of the downward trend that happens when there isn't a lot of precipitation going on, they can kind of understand that. They don't really understand that precipitation is tied to this huge jumping kind of, that's kind of hard to see, but basically the actual value of the river there shoots way up, like way up here, and the model eventually starts to go up there, but in that case, though in other cases it doesn't. This was actually where I studied kind of comparing four models. But anyways, I guess the takeaway of that, there is a link in the slide, so if people want to read through this whole report at some point they can. But the main takeaway for that is just don't always trust your metrics and always look at kind of what values your model is using when forecasting. So you should even look at those shape plots and even play with different values of variables you know it's dependent on. Okay, so now we're actually going to jump into some code and some code examples of using flow forecast to forecast. And these are publicly available on Kaggle, so anyone can go back and see these later. I don't know if I'll actually run this now or not. Or do people want to actually see this run in real time?
Of course.
Okay. I'll run through this again. So basically here, again, this is in a notebook. At the moment, well, you can install flow forecast using pip too. The moment I'm installing most places using the master branch, just because I've been pushing a lot of stuff to master recently and haven't necessarily released into a package, which I probably should do. But anyways, that's basically just downloading and installing flow forecast, which would also be done by a pip install. So we can run that. It will run in that cell, generate a lot of output. Then basically, so this data set, it's a, for all things considered, it's a pretty simple data set. It's not, we don't really have the problem with a lot of missing values. We don't have tons of variables. The only thing we really do have that's somewhat, okay, it finally started running. The only thing we don't really have that a lot of that might be challenging is it does have different regions in it. So right now, in this first example, we only train a single model to a region. In one of the, I actually have different examples of how to do this. So in one of the later examples, I'll actually show one where we train a model on multiple regions at once. But anyways, this one we're just training one to a region. I think this is going to run. It's still installing. So once that runs, basically, I'm just doing basic data. Typical data stuff. So here, as I said, we're limiting to one geography because obviously we can't just feed in the whole DF with a bunch of different geographies at once unless we specifically tell the model we're forecasting on all those, which makes it more complicated. So, and I'm also only looking at a single type. But this is another actually interesting thing to think about is that oftentimes when forecasting, we're trying to forecast on different regions and different resolutions. So we might be forecast, well, at least most people probably work with some geospatial data. For instance, when I worked in retail, we had different stores and we tried to forecast for different stores. Or you could forecast for like a whole county of all the stores in a county. So like deciding your, I guess, your geospatial region, if you do have this type of data, is sometimes useful. Because sometimes you might not have data for each location or a lot of it, so you might actually want to combine stuff into like a higher resolution and try to do it on, I guess, everything at once. Anyway, so that's kind of what these cells are just doing. Also, I'm only forecasting one type at a time in this example because different types have different costs, so I don't want to confuse this. This will be a fairly simple model, but I don't want to confuse it with different types. Trying to forecast two types at the same time. And now we get to kind of the core part of flow forecast and why I think we're kind of a unique framework. Everything in flow forecast, we use a configuration file, and this helps both with reproducibility because we always know what exactly hyperparameters we're using in the configuration file. Because as we run this, the configuration file itself will get logged to weights and biases. So we'll always know which runs generated which results. So this is basically the configuration file. Here I'm just using the model name DARNN, which is basically an RNN with attention. Well, actually, it's actually usually an LSTM or a GRU with attention, but they called it RNN. But it can be either one. So here are our model parameters. So we're using essentially 6 time series in total. We're using the average price, the total volume, and these are different amounts of bags sold. Wait, actually, yeah. Oh, yeah. So, actually, yeah. Here we're using we're actually using 5 time series here, I think. But we plug in 6 to DARNN because the 6, DARNN has this quirk where it's the 6 that you usually is basically you have to pass an extra value to that for the target. Most models in flow forecast though you pass the exact number there. That's but it is documented here. So in any case, that's how you do it. We're going to use these are fairly standard values, but these could, as we'll see in other examples, be tuned by a hyperparameter search. So this is the hidden size for the encoder, and this is the hidden size for the decoder. The number of output features is 1 because we're only forecasting one target here. And then we're essentially taking 4 historical time steps to forecast 1 future time step here. So we're taking 5 historical ones and forecasting 1 time step into the future. These finished running? Yeah, I guess they did. So that's basically that part of the configuration file. Again, these can be changed. So this can sometimes be a tricky hyperparameter to figure out how many historical time steps will make for the best forecast. Because at a certain point, like in the very far past, it might stop mattering. And if you put in, say, like we did like 100 of these, like after a while, like some of those really far ones, the model might think are important, but they're actually not. So I usually optimize this in a hyperparameter search. But here, again, I'm just using 5 for kind of a simple example. Now the data set params, similar, we just specify the batch size and all that, train end, train start, target column, sort column. Some additional parameters, like if we want to scale the output. Oh wait, yeah, I misread my own configuration file here. The reason actually why this was 6 time series and not 5 even though there are 5 specifiers. Here we're actually generating an additional parameter, so we're using the month as a numerical feature. So actually in flow forecast, you specify both the columns in from the data frame you want to use, and then also if you want to generate numerical features automatically, you can do that with by including this feature param. I like to do that because then I don't have to do a bunch of manual things, slicing up this thing here. And these are weekly. The data here is also reported on a weekly level of granularity. So that's why I'm using month as kind of a feature. But you could also, if the data had it, like in the feature params include something like the day as a numerical feature, or even something like the day of the week, and all you'd have to do that would be to include day like numerical. You can even do hour too. It all depends on the granularity, and then basically our code will automatically generate those features for you. But yeah, then you do have to remember to add essentially however many you are to the number of time series when initializing the model. So yeah, I actually misread that there. Anyways, going down, we have training parameters. Actually, I'll just run this cell now so this thing can get started training. And then we can keep talking while it trains. So yeah, then again, we have learning rate. Here I'm specifying a fairly low learning rate, 0.001. It's not the lowest. Some models, particularly big transformer models, you'd actually probably want to go 0.001. Because those take a really, if you ramp up the learning rate too early, they'll fail to converge at all. Anyways, that's kind of the configuration file. All this is documented too on our, basically we have a Confluence page of documentation where we document how to use configuration files. Basically training, it goes over the different parameters, and there are a bunch of different parameters you can add. And the nice thing is like if you want to change something, like say how you're scaling the data, all you have to do is change that scalar parameter. If you want to add more columns, so if you started off really simple, we're just using 2 of these, you just delete these columns and change the number here. So it's pretty simple to play around with a lot of different settings. So I think that cell below did finish running, or it is running. So basically, results, we have it set up to automatically log the weights and biases. You can create your own weights and biases account for free. There are also private settings on weights and biases. So if you have a confidential data, you can make the private. All these are public, so anyone can look at them. But you can make them private. There are teams too for companies on weights and biases as well. I'm not pitching weights and biases, but I do like to use it for logging experiments because it does make stuff easier. So that's why we built in kind of a native integration here. So there we can see some of the loss. The validation loss didn't necessarily go down as quick as the loss. And then we can scroll through here, see different heat maps of what the model's looking at. So it looks like most of the case it's using the total volume sold as a heavy predictor. Doesn't look like it's really using these other features at all, really. The SHAP isn't 100% reliable. Anyways, but then here again we have our prediction versus the actual. So these are what the model predicted. Looks like the model predicted pretty straight. This isn't that off. This is predicting, I guess, 1.5 here. It's predicting 1.22 here. Again, remember we didn't really tune any of these parameters at all. We just kind of, these are kind of a default setting that I was using. And we're not really using a confidence interval otherwise. You can also generate more plots easily too if you want to look at it on different dates. Oh yeah, I forgot to mention the configuration file that determines what date in the test set it will plot on. So like here, the date time start is like November 1st, 2020. So that's where it's plotting from on the test set. That's where these predictions are starting on when it's plotting here. And then hours to forecast is actually, this should really just be time steps to forecast, but this is a remnant of when it was strictly used for river flow forecasting. I should probably change that in the code base at some point, but this is basically now just the number of time steps you want to forecast. So in this case, it's actually forecasting 5 weeks into the future. The other cool thing is we can actually specify multiple metrics at once. So here we're actually recording 3 metrics at once. Of course, you can only optimize on 1 metric at once. Or else, well, you can actually do it with multiple ones too, but you probably wouldn't want to do that. But here we can specify multiple metrics for it to plot on the test set. So there we do see things like, we see the dilate loss, we see the L1 loss, and we have an MSE loss too. So yeah, and then like, likewise, then if you do say like 10,000 or 1,000 runs of different parameter configurations, you could then sort by like the different losses and get the one with the best loss. So for instance, then you could add a filter and sort by these. Or yeah, actually, you want to sort here. So that's another reason we log to weights and biases automatically, is it just makes it easier to deal with runs and things like that. So there we see that. And then again, as I said, it's pretty easy to use our built-in plot functions if you want to plot additional plots. So for instance here, now let's try like plotting. This is still in the test set too. You would want to check, of course, like you're actually plotting dates in the test set. Here actually I divided train and test stuff by the length of the data set. So this is the train start, train end, valid start, valid end. You can just specify numerical things there too. And then, so yeah, now we can plot here. We should be able to see a plot. We'll just regenerate it. Yeah, again, yeah, just doing this. Sometimes other weird stuff happens too with various random speeds. We trained this using MSE, actually. Oh, we actually trained it using dilate. But yes, where sometimes actually random seeds can influence how the model works too. So I think I've run this same configuration a couple of times, but gotten slightly different results just by how it's been initialized. And that particularly happens on smaller data sets. Like once we like trim this down, we're only training on 306 rows. So basically, the initialization of the model weights will have more impact. On a larger data set, that will be less of the case. And you can actually, we're building something to actually freeze seeds automatically, but you can set the seed manually in PyTorch using a seed scene too. Anyways, that was kind of a very simple example. I have a couple more examples on this same data set of doing slightly different models. Gotta remember where I put them exactly. Avocado. Okay, yeah. Here I actually I won't run through all of this exactly, but here again we changed the model slightly. Basic same pre-processing here, but here we actually use what's called a probabilistic. So we use a probabilistic deep model. So we're actually predicting kind of the mean and standard deviation instead. So similarly, we have our same kind of configuration file. This is basically the same, but here we're using a GRU, which is another model available, and we're making it probabilistic. So we're setting this probabilistic parameter to true. Yeah, pretty much the rest is the same. through here. You know, you do that, you train it. But yeah, the nice thing about a probabilistic model is then it basically, at the end, it creates a distribution, and then you can sample the distribution. So then when we look at these plots, we can see, you know, here's the actual average price. Here's what the model predicted, but here are the upper and lower bounds of essentially the distribution. So again, we didn't really do that much. I didn't really do that much extensive hyperparameter tuning on it. So you can see that the lower bound is kind of ridiculous since it's in the negative zone. But it does show the model is pretty is pretty certain that this is where essentially the average price will fall. You know, hopefully with parameter tuning we could narrow that. So this is the plot on another date. Here are predictions. Not that far off actually. And then here's the upper bound where I think the max price could be, in the lower bound too. So that's kind of a probabilistic example there. And I have one more example using that same one code where I think I called it multi-region. Multi-region transformer. So here I actually use a transformer model. Here I do take out the transformer. The thing I do different here is I actually then predict on two kind of geographic regions at once. So here I predict both on, I think it's Chicago and Detroit. It's still a little messy using flow forecast for predicting multiple geospatial regions at once. Though hopefully I have a PR that's going to simplify it. So you still have to do a lot of the features by hand. So here I merge them and I kind of create this combined thing into this combined data frame that encompasses both the Chicago and Detroit things. And then I just like map it to this. So this is Chicago, CH stands for Chicago, DT stands for Detroit. Then I feed these features in to the model. So and then again, of course, since now we're forecasting for two things, our output dimension is 2. And then every model has slightly different parameters that you put in model params. You can see those in our read the docs page. But of course here we're now forecasting for 2 targets, so we put 2 there. And yeah, then we basically just run this again. And again, we'll plot some of the results, but now we'll actually have 2 plots. So this is the, oh yeah, the other thing I did too here is I added a confidence interval. So even on non-probabilistic models, using dropout, you can do a confidence interval because dropout zeros some of the layers. I don't know how familiar people are with dropout, but there was actually a deep learning paper like a couple years ago that argued dropout is kind of a way of almost doing Bayesian kind of inference on deep learning models. I don't know how true that actually is, but you can get a confidence interval somewhat at least using dropout. So here I do put dropout at 0.1. The bigger the dropout, the more of the layer it zeroes out randomly. So the more dropout you put in generally, the bigger the confidence interval you'll see. And then you'll also dropout can help prevent overfitting on particularly small data sets. Then we also have this number of prediction samples param. So basically it runs the model 20 times through, and then it creates that confidence interval. It's still a bit different than the probabilistic one because the probabilistic one, we're actually training the model explicitly to predict the distribution and the STD using the actual loss function. This, we're still just training it to predict one target, but then we're running it multiple times later to get the confidence interval with the dropout. So we're not really training it to be a probabilistic model. But anyways, here's kind of this. This is the confidence interval. I forget, is this one Detroit or Chicago? Now I should probably label that here. So this is, oh yeah, this is Detroit. Looks like it did better learning Chicago, at least a bit, but I didn't really get that valley there. Didn't do that well in that part of Detroit. But I think this is important too, like in time series, too often people don't just like look at their metrics blindly, or they look at one kind of cherry-picked example of like how the plots are, but really looking at different plots and seeing how it performs under different kind of date times is kind of interesting. So yeah, a disadvantage here is it doesn't really seem to get that price is high here. But yeah, often when you plot, like I found even the best of the models multiple times, like some of them will be way off, and then you have to try to dig in to figure that out and stuff. Okay, so again, as I said, this I didn't really optimize in terms of hyperparameters at all, too. Okay, so that kind of covers the avocado forecasting examples. Oh yeah, I actually had an example that I thought worked of time series classification, because flow forecast can actually do time series classification. Then I realized actually just the other day that this was a bad example, because as I was training it, I realized my ROC curves were all over the place. And then I realized actually these human activity recognition data set, the human activities, the lengths of the number of frames in each are basically irregular. So sometimes there'll be 20 frames, sometimes there'll be 30 frames. So basically the model is learning nothing. But if the frames were the equal length, this is how you'd set it up. And you can see you basically set it up. A classification, you'd set number of targets equal to the number of classes. You use this general classification loader. And then, yeah, pretty similar, except then you use like a cross entropy loss for classification. But yeah, basically here the major problem was, and we'll see that basically the model didn't really learn anything over time, because the ROC curves don't really change that much as the model's being trained. They basically stay pretty static. And the loss is very funky. And this is because essentially, and it goes back to one of my earlier points about knowing your data, because here I was just like, oh, I'll cook up this example really quickly. And so I just assumed all the lengths of the different activities. So there are these different activities, standing, walking, etc., would be the same length. And in reality, they weren't. So actually, probably in reality, forecast should throw an error here. It should throw an error message or a warning, warning people about this, so it just doesn't run. But again, that's a good example of why you have to look at your data carefully, I guess. But yeah, you could use this as a template. You know, I often will copy config files and then just plug in my parameters to them. So like if you were doing a classification problem where the length of the sequences you're classifying are the same, this template would kind of work for that. Obviously, it doesn't work in this case, though. Okay, so that was the bad classification example. So now we can go to another full this is kind of a full hyperparameter sweep I did a while ago. And because it's a really long thing and took forever to run, we obviously won't run this full thing, or we could start running it, but it won't finish. But basically here, again, this is forecasting a river flow, first of all. So I have these, just show you some of the data to give you an idea. So we have these like big things of river flows. I wonder if I can actually, maybe I'll download some. I don't know if I can pull that up. Full width. Okay, there. So basically we have precipitation, temperature, dew point, things like ice accretion. I don't really use those columns. And then we have the cubic footage per second, which is footage. Go back there. Where'd my notebook go? I don't know how Kaggle's exactly rendering this. But anyways, from that file, we basically, again, select the cubic footage per second, the precipitation as relevant columns. And then we're trying, actually here, because we wouldn't necessarily know what these would be ahead of time, I'm using all these as target columns. So here this model tries to forecast all of these at once. Which is obviously harder to do, though in some cases if the data set is big enough, then these can actually be pretty good like auxiliary columns, because the model can better learn the relationships by forecasting multiple ones at once. I don't, it somewhat, I think, works here, though it doesn't work that great, as we'll look at when we look at the sweep results. But then kind of getting to the hyperparameter sweep. So you can see also here, instead of just putting specific values in here, I'm actually putting in stuff from another configuration, which is the sweep configuration. So these are different parameters we want to sweep over. So we will sweep over batch size 200, 400, different number of layers, different learning rates, different forecast history length, different number of kernels, different dimensions of the model, and different amounts of dropout. So yeah, that's basically, that's what happens there. And then we can go to this sweep URL. So I think this sweep, oh wait, this might have been one of the ones that failed. I have a bunch of ones that succeeded. So so this one ran essentially 116 different configurations. And so we can see, compare different losses from different models. And since we're forecasting 4 things, here's different models trying to forecast the temperature on different days. There's different models trying to forecast the dew point. Some are doing it better than others. But again, yeah, we should be able to pull up some of the better models. So you can see there's a wide variety of actually different forecasts based on those hyperparameter selections and stuff. The hyperparameters really do matter. So we can actually sort these by test loss to see what in series should be some of the better models. I'm going to go make sure I select the right type of test loss there. So it looks like our test loss was
penalized.
That was our criterion. I don't know if I plotted a different loss though. How did I put metrics? Oh yeah, we just use regular MSE for this. So test loss.mse. So this in series should show some of the better models now. So this one doesn't look that good. Well, see here we can see it has pretty big confidence interval. So it doesn't really. But actually, this is somewhat useful because this is actually forecasting 336 time steps into the future. So you can see initially it's pretty certain that the prediction should fall, of dew point should fall in this range. Then as it goes on, the confidence interval gets wider and wider. So actually that's not really that bad per se, I think. Yeah, and again, here's cubic footage. It looks like the prediction starts off really close. but then over time, the confidence interval gets wider and it gets further away. It's not able clearly here to predict precipitation well. But precipitation is kind of a hard thing to predict without, I think, more geographical figures, because it will suddenly be zero, then have a huge spike like here. So yeah, that's kind of an example of that. So we do see that like some of the better models. That's weird how the actual loss shot up for a while here. That's the only thing I wonder about with this model. The regular. So we can see, though, that some of the predictions it made were good, and its overall test loss is low in the end. So that might be a model we might want to investigate further. Though clearly it's still probably not great for very long range forecasts. Like I don't think that's very useful for that many time steps into the future. Anyway, so that kind of covers, I guess, some different examples of using flow forecast. I guess now I'll go finish the rest of my slides, and then we can go over, have a nice long Q&A session. And then, yeah. So, okay, so that was what I just showed. Future directions. So, you know, we're always seeing bigger, better kind of deep learning models come out, but I actually think some of the, and these can be appealing in a lot of ways, but I think some of the cool stuff that's actually coming out that might help some of these problems more is on the end of like knowledge infused models that are actually a synthesis of deep learning and kind of and things, because there's still a lot of basic intuitive knowledge that neural nets are often getting wrong, even some of these really huge models. We don't all have huge data sets, so yeah, so again, future directions. I do think forecasting multiple regions at once is going to become a lot bigger. Or at least there already are models that do that. I'm just working on getting the data loaders to work right in flow forecast, because it becomes more complicated with the loss and everything when you do that. So I'm trying to put it, so our framework automatically does that and you don't have to worry about that. But then as I was saying, the move towards hybrid models, neural ODEs, fusion of knowledge. You know, one of the cool models I remember from when I worked on the COVID forecasting was they actually did a hybrid of the SEER model, which is an epidemiological model, and a neural network. And I think that by far, the group that came up with that outperformed any of the pure neural networks or the pure epidemiological models. So kind of a neural network that can then estimate some of the parameters of kind of known differential equations or other models is really useful. And likewise with the stream flow forecasting, I think that might help with the model not really, you know, as you saw even with some of the better models, it didn't really know that precipitation, because it rains so little, would like cause the river flow to go up, which most of us could intuitively say. So like a neural ODE might be a lot better with that. They can also help for kind of irregularly sampled data. Then again, models that can synthesize non-temporal data or other modalities of kind of data. So over time, we're going to actually, I think, see a confluence, because most things, if you think about it, have a temporal aspect. Like you could have words that change over time too, or text data sets, or like obviously video. So I think more time series forecasting methods have been almost exclusively kind of numerical to this point, but you're going to see a synthesis of more modalities of data into them, which is a really interesting research area. Of course, with that, there's going to be a lot more complexity. And finally, graph neural networks. I really like some of the recent papers on graph neural networks. Unfortunately, pre-processing data to be in that vertices format is very complicated and confusing. I'm hoping at some point to also integrate that into flow forecast so it's more intuitive. But there have been a lot of great kind of results from GNNs of learning these geospatial temporal dependencies. Well, and you know, a lot of time series problems do have some spatial component where you have different time series in different places, or even, you know, even like something that isn't like geospatial, you might have some spatial component. Oh yeah, I guess one more thing I'd add too is I think another big area too, as I said, is also, I didn't list it here, but also interpretability methods. I kind of touched on some of that with the SHAP stuff, but SHAP still isn't great with interpretability. So I think we need better ideas of like what the neural networks are doing at each individual layer. Because I've actually checked some of my models, and sometimes even a bad model, like the representations are really good, the intermediate representations, if I look at specific layers, are really good, but then the end forecast comes out bad, so it's interesting to see why there's the disconnect there. So yeah, anyways, that's kind of it for my structured presentation, but yeah, I definitely want to delve into questions and stuff like that. So.
That was awesome. So yeah, I'm just going to pass this microphone around. Any questions we have?
You mentioned that the performance between models can be hugely variable and depends on the data you're talking about. If you're trying to predict a thing that you do not know yet, which is what makes these valuable, is there a principled way to pick one versus another based on the shape of the data?
Yeah, well, so it really depends both the kind of, I guess, shape of data and how much data you have. This thing, yeah, basically the large transformer models really take a ton of data to make them work well. So for me with transformer models, unless I have usually at least 50,000 rows or something, I don't even bother to begin looking at them. I mean, you might do more or less, but that's kind of been my rule. Also, I think a thing with transformers is if you do transformers, you have to accept that you're going to spend a lot of time hyperparameter searching and stuff. Like you might spend days of that. Like I think sometimes transformers in the end might outperform, some of these basic like GRU or LSTM. But like the question is like how much compute resources do you want to use to find like those exact like hyperparameters that work. So. Question back here?
Yep. Thank you so much for the talk. And for like specifically irregularly spaced data on what is the point, what is the advantage of like using neural network model as opposed to let's say like Gaussian processes. So like does it make sense to maybe like apply Gaussian processes to kind of like infer the unsampled area and then apply the neural net model?
Well, yeah, neural networks can work on. Wait, were you asking about variable length data or regularly sampled?
I would say like irregularly sample like
yeah.
Data points of like other data points of like
Yeah. Irregularly sampled data right now I think is pretty hard for neural networks because there's at least some structure to the inconsistency you need in the shape for them. There was a good paper, as I said, on the neural ODE front. They created a GRU that also used kind of like an ODE, and it was able, I forget exactly how it was done, but it was able to actually overcome some of those limitations. But that's the only real success I've known of using deep learning on really irregularly sampled data. So like in that sense, like I think Gaussian processes might at this point still be easier. But I think over time we might see more models that address that. So.
Cool. I actually have a question also. So some of the data I deal with has multiple levels of seasonality. So you have 3 different types of seasonalities at the same time. And I found a lot of the classical models aren't very good at dealing with that. Have you found a way to deal with that with these kind of more complicated neural network models? Or does your package do that?
Yeah, well, I guess part of it is going to be the features you generate from those. So like as I said, you can generate those different daytime features, and you can also there's a way to generate them cyclically, so they're like sine and cosine, which helps a bit. Though really for neural nets to learn seasonality, they need to have like a lot of examples over time of that. So like obviously you only have data for 1 year, and you try to train like a neural network on it to learn like say Christmas shopping patterns, is probably not going to do that well. So you do need to feed a lot of data into it. So
Any more questions? Oh, sorry.
Thanks. I guess for some of these future models, this is going to be everybody needs a supercomputer, everybody needs like 5 GPUs in their laptop. Some of them are going to be require less compute maintenance. What's your thought on that? Or should we all just go buy crypto mining stuff? I mean,
yeah, I mean, I think to train one from scratch, they'll probably require us a ton of compute, obviously. I think what will happen probably as we get a bit better at like transfer learning and other stuff in the time series space is it will probably converge to somewhat like BERT. I'm still waiting for them to come out with an equivalent, but I think over time there'll probably be these pre-trained models that we'll often use, and then we'll fine-tune them to a different time series task. That would be my guess. Though so far it's proven more difficult, I guess, to do that type of transfer learning in time series than in NLP. But I still think it's heading that way slowly. So.
Cool. Also, just a comment. A lot of the stuff here was run on Kaggle notebooks, which have GPUs. You can just access GPUs for free. So I've always found it to be a good resource. Cool. Any other questions? Once, one twice. Cool. All right. Let's thank Isaac again.